All right, so CBC looks like that. So who wants to tell me how does how do you draw the diagram for ECB? So obviously we've got, so let's draw a few of the things that we know would be there. So we've got the plain text, right? So that's still P1, P2, P3. We've established that ECB is insecure, right? So, okay. And then down here, we want to have C1, C2, and C3. Okay. So we've got C1, C2, C3. If you look at the previous one, we have the encryption, we have an XOR operation, we know the key is involved. Okay, so it's going to be something like that. Probably XOR the encryption algorithm, whether it's DES or AES or something. And we've got that. All right. So now what's the difference? Who wants to tell me? So we've got the key. Where does the key go? Same place. Okay. Same place as CBC. Good. So that's the key. Right? And then what else do we do to CBC or ECB? What else do we do? The arrows, right? Yeah, okay, sure. Yeah. So these arrows, right? Good. So plain goes into the XOR. Basically, we XOR with the key, and then we get C1 and C2, C3. Anything else? Or have we arrived at ECB?
No, that's it.
That's ECB, right? That's it. So you guys see the difference now? They're independent, right? There's no connection between this and this. Do you see that? So what's the problem? Key is the same. Oh, yeah, go ahead.
I just have a general question on
Yeah.
the key.
Yeah.
If you have a key that is, so I'm assuming the key just gets turned into zeros and ones.
Yes, sure.
If you have a key that is longer than the plain text, what does it do?
If you have a key that is longer than the plain text, then and it's totally random, then you've achieved perfect secrecy. That's the one-time pad. But it's impossible to have that because what if you're encrypting a movie for Netflix? Are you going to have a key as big as the entire movie?
No.
No, right? What do? You have to break the movie, the Marvel movie or whatever it is, into blocks and then encrypt with a key of size block. Do you see that?
Well,
You couldn't send, you'd have to send, it's like sending the entire movie again as a key. You'd have to do that.
okay.
It's very exhaustive. Imagine that's not duplicating all the network traffic in the world, basically. Plus the operation of actually doing that on your CPU, etc. Do you guys understand? So yeah. Oh yeah, please go ahead.
So like we talked about earlier, I think it's, so the key has to be the same size as the block.
The key has to be, so there's a difference between if you use OpenSSL, you don't know how it's implemented. But if you're writing the code in Python, you have to do so that the key is the same size as the block. If you remember, we actually did a for loop and we index, like we grab 1 0 and 1 letter, that kind of thing. So they were the same size. Any other questions? Right, so we've already done a little bit of this with the XOR example, then with the hash example, and now we're just going to do a third implementation of this one, but we're not going to implement ECB in code. We're going to actually implement CBC. Yeah, go ahead.
So for the individual blocks,
Yeah,
each individual key is different.
right? Or is it the same?
Is the
key?
same key.
Okay.
Think about that question. So if this was, let's say this is the letter A or AA, and this is AA, right? So that's in ECB. The problem is if this is the same, then this is going to be the same. Let's say EF, right? I'm making up some hexadecimal, for instance. But if you use different keys, then what's going to happen? This will not be the same anymore. You see, you'd be using like a mechanism of having, but then that's almost like going back to this idea of a key as big as the message, because you're using so many keys to, so it provides more security, but it's just not practical. Yeah, please.
But would that also apply to CBC or no, because of the ID would make the first one different?
Right. The CBC, what CBC does, and you've seen it already in the image, right? When you encrypted that image, there was no pattern anymore, right? But the all that happens is the mode of operation does this. So you get, you know, it actually, to you, your example is kind of good, because what we're getting at, what if I use different keys for every block? Then I'm going to get better security, right? But that would not be practical, because then you have to send a gigantic key. What's the solution? Well, you don't need a key. Just send one key, and then one key here, and it's the same key for all, but you take this plain text, XOR it with the key, and now you have C1. Use that in the next one, and so it's going to change it. You see that? So each one is feeding into the next one, and it's in a way acting as a pseudo key, different key. Yeah. You guys get it? Any questions on this idea? Yeah, please go ahead.
Okay, so for ECB, like if the key is at the same size as the message, how does it XOR those like missing bits?
So okay, let me for ECB or CBC?
ECB.
For ECB. Okay. Say the question again.
Like if the key is a different size than a message, how is it XOR if like they don't line up?
You mean the block or the whole message?
Like the block. Yeah.
The block. They should be the same. Otherwise, you'd have to handle that in your code somehow. So for instance, if the key is bigger than the block, the plane, then you could do padding. That is what we actually do with the last one, right? You could do that.
But you said like for open SSL, the key is different.
Ah, okay. So yeah, I would think that OpenSSL probably uses like if the key is 16, then it's gonna keep track of it somehow.
Okay, so it's like the block size.
It would change like the block size. It might do padding or something. So there's something in the algorithm that handles it. Yeah. You just want to be consistent. So like if your keys are, because you have some control over this, right? If the key is, let's say 16 bits, which is what you define, and then you're going to say for whatever reason, okay, I have a message, you can split it into whatever you want, but let's say you decide I want to split it into just size 8, right? So the information is there, but for you to XOR this, just for the math to work, right? You could cut the key in half, but then that loses some security maybe. So padding might be a good idea. And then just remember in the end to unpad it and just recover this part as the message. So it's something that you can control in the algorithm. Any other questions, guys? Nope. All right. So we did CBC, right? So there's another one, which is called, we're just going to look at this one. Now, I'm not going to give you the proof as to why this is secure in this way, but we're just going to talk a little bit about it just to complete CFB, another mode of operation, CFB. We're just going to look at it. We can talk about it a little bit. This one starts for the cipher feedback mode. Cipher feedback mode. Again, remember, these are not DES or AES. They're just modes of operation, right? How you chain the blocks and the keys and all that. This one also uses an initialization vector. Okay, and it's like CBC. So here we start with the initialization vector here. Okay, so the initialization vector goes in, and then we have the encryption algorithm here, which is going to be the XOR operation, and the key comes in here. So I'm just going to write key. And then from here, you have an XOR operation, and your plain text message will come in here. And then now you get C1. So if you look, this one's a little bit different. This is more, just a little bit different. So it's almost like the key is somehow accumulating more complexity, if you want to think of it that way, right? It seems like there's this like an accumulator in a programming language that's changing that key. Because if you look in the next one, we're gonna have now the encryption XOR operation, right? Encryption, and then the key still comes in through here. Key, but now this ciphertext goes in through here. Do you see that? And then, as you might imagine, this comes down. You have an XOR operation here, and I should have said plain one here. Okay, that's the block one. So then, obviously, this one, and actually, let me draw it down. Then this one would be plain two. You guys see that? And that goes into this XOR, and that gives you C2. So if you look, it's a little bit different from the other one, right? And as I said, it gives this feeling of like the initialization vector, the key, and then that thing that you're using as a key just keeps getting more complex. And then just draw one more for completion. And that's going to be E, right? This is encryption. And that's C3. C3 comes down here. Plain 3 goes here. And then this one, of course, goes like that. Does that make sense? Do you see the difference? This one, I mean, the argument, it's like a stream cipher. Do you guys remember what the stream cipher was? We would take a byte of the key, let's say, and a byte of the message and XOR those and send it our way, right? That was the idea of stream cipher. In a sense, this is the same, but in blocks, because you get like the block of the message, and then you get a thing to encrypt with, right? And then you get the next message and a thing to encrypt with, the next message or plain and a thing to encrypt with. But it's not at the byte level, it's more at a block level. Okay? And this includes the key always, it includes the initialization vector, and the result of this XOR operation. All right, and this is the cipher feedback mode of operation. Okay, so with this in mind, actually, because this kind of leads into this idea of stream cipher, I suppose. So let's go over stream ciphers. Okay, so just to kind of give you some, I'm going to give you a formalization of that as well. Okay, of what the stream cipher is with relation to the block cipher. So let me see. All right, so let me actually, for this one, because it's a slightly different